Hello, my name is Michael Pont. In this presentation I'm going to discuss the use of a TT wrapper to meet the challenges of SOUP in medical systems. In this talk I'll be discussing the development of embedded systems in compliance with International Safety Standard IEC 62304 and IEC 61508. In this presentation, I'm going to consider what IEC 62304 is. I'm going to consider what SOUP means. I'm going to consider the links between IEC 62304, IEC 61508, and time-triggered or TT architectures. I'll consider the challenges of SOUP, how the challenges of SOUP can be addressed by implementing what's known as a TT wrapper in your system, and I'll present my conclusions. So the first thing I'm going to consider is the development of embedded systems in compliance with IEC 62304. So the version of the standard that we'll be considering in this presentation is IEC 62304 2006 with Amendment 1 dated 2015. I'm just going to call it IEC 62304. IEC 62304 is concerned with the development of software for use in medical devices. The standard notes that software is often an integral part of medical device technology. It notes that the effectiveness of a medical device that contains software requires knowledge of what the software is intended to do and demonstration that the software will meet such intentions without causing unacceptable risks. IEC 62304 requires that the manufacturer of the device assigns a safety class to each software system. This is going to be Class A, Class B, or Class C. These classes are assigned based on the impact that failure of the system may have. So Class A systems are not safety related. No injury or damage to health is possible if these systems fail. In Class B systems, these are safety related. Non-serious injury is possible if the system fails. In Class C systems, death or serious injury is possible if the system fails. These classes are fairly standard across other international safety standards. They don't just apply in 62304. So in summary, Class A is not safety related, Class B is what would usually be called safety related, and Class C is what might be called safety critical. In this presentation, I'm going to be particularly concerned with what is called SOUP. IEC 62304 defines a software item that has already been developed, is generally available, and that was not developed for the purpose of being incorporated into a medical device as SOUP. SOUP stands for Software of Unknown Provenance. The use of SOUP is considered extensively throughout this standard. One reason that use of SOUP is considered throughout 62304 is that some medical systems rely in part on the use of commercial off-the-shelf operating systems, COTS operating systems, such as Linux or Windows, and it would not be practical to rework this software completely. Overall, it's probably fair to summarize the approach in IEC 62304 as one of segregation and containment of SOUP. That's segregation and containment of SOUP. If I summarize the requirements in this standard, the user of SOUP, that means the developer, must specify the functional and performance requirements of the SOUP item. He or she must specify the hardware and software requirements of the SOUP item. He or she must identify the level of segregation necessary for controlling risk. and he or she must verify the software architecture to ensure, for example, the correct operation of any soup items. We'll return to these steps shortly, once we've considered the more general requirements for software development in compliance with IEC 62304. So in the remainder of this presentation, we'll explain the links between IEC 62304 and IEC 61508, explain the links between IEC 61508 and TT architectures, explain briefly what a TT architecture is, explain briefly what a TT wrapper is, and explain how a TT architecture can be used to wrap up soup. So let's begin by looking at the links between these various standards and TT software architectures. IEC 62304 is intended to be used together with other appropriate standards when developing a medical device. In particular, readers of this standard are encouraged to use IEC 61508 as a source for good software methods, techniques and tools. You may be familiar with IEC 61508. This is concerned with functional safety achieved by means of systems that are implemented primarily in electrical and/or electronic and/or programmable electronic technologies. Typically these days what that means is that IEC 61508 is concerned with systems that are usually implemented primarily using microcontrollers or other forms of embedded processor combined with appropriate software. IEC 61508 is a base standard from which various other standards have been derived. For example, ISO 26262 is a very influential automotive standard which was derived from IEC 61508. Time-triggered, or TT, software architectures are recognized as providing a highly effective way of meeting IEC 61508 requirements in many cases. For example, time-triggered architectures are highly recommended for systems of safety integrity level 2 or above in an IEC 61508 design. If you are not familiar with 61508, a SIL 1 to SIL 2 type design is roughly equivalent to a Class B design in IEC 62304, whereas a Class C design in IEC 62304 would be roughly equivalent to a SIL 3 or SIL 4 design in IEC 61508. So TT architectures are highly recommended for systems of safety integrity level 2 or above. Use of a TT architecture is found to greatly reduce the effort required for testing and certifying the system according to 61508. Static synchronization of access to shared resources, a key characteristic of all TT designs, is recommended for SIL 3 and highly recommended for SIL 4 designs in IEC 61508. And limited use of interrupts, which is a defining characteristic of TT designs, is recommended even for SIL 1 and SIL 2 systems in 61508 and highly recommended for SIL 3 and SIL 4 systems. In very brief summary, a time-triggered software design is usually implemented as a bare metal software platform. That means there's no real-time operating system, no Linux, and no Windows employed. There's just one active interrupt per CPU linked to a periodic timer tick. The peripherals in the design are polled. They're not controlled by interrupt handling. Overall, this is a very simple architecture, and it provides two key benefits. We can model the system behavior precisely at design time, and we can detect changes to the system behavior at runtime. You'll find an introductory video on TT systems on our website, and the full URL is on the screen. So now I'm going to look at how we can meet IEC 62304 requirements by using a TT wrapper. So if we go back to the key 62304 requirements, the user of SOUP must specify the functional and performance requirements of the SOUP item and specify the hardware and software requirements of the SOUP item. So to meet these requirements, we need to document the SOUP item and its operating environment as fully as possible. The next IEC 62304 requirement for dealing with SOUP involves identifying the level of segregation necessary for controlling risk. What this means in practice is that we will usually have a separate monitoring and control processor that's implemented using a TT wrapper, and we will keep that monitoring and control processor distinct from the processor or the processor system that's running SOUP. We'll say a little more about this in the next few slides. The next thing we have to do is we have to verify the software architecture to ensure the correct operation of any SOUP items. To meet this requirement, we need to perform a test and verification process in order to demonstrate that the TT wrapper can address any problems that arise in the SOUP. One of the reasons for using TT software in the wrapper is that such a test and verification process is greatly simplified through use of this architecture. For example, as IEC 61508 Part 3 notes, use of a TT architecture greatly reduces the effort required for testing and certifying the system. So now let's consider how we can meet IEC 62304 requirements through the use of a TT wrapper. I'm going to consider in outline a specific example. Suppose we have some form of medical infusion pump. We have our processor running SOUP, and we've got SOUP outputs generated by that processor. And these SOUP outputs, we assume, are intended to control the infusion pump. Now, as things stand, because this is SOUP, Software of Unknown Provenance, we know that we cannot safely drive the pump directly from the processor that's running SOUP. So let's take the processor running SOUP, and what we would do in these circumstances is feed the outputs of this processor, feed those through the processor running the TT wrapper software. The end result of that would be a set of verified outputs which would then be fed to the infusion pump. So at the simplest level, what the processor that's implementing the TT wrapper is doing, what our TT wrapper is doing, is it's doing sanity checks and checks on the outputs from the processor running SOUP to make sure that these can be applied safely to our medical infusion pump. Now within the processor that's implementing the TT wrapper, we'd have a standard software configuration that we call a correlator platform, and this would ensure that the TT wrapper can perform continuous self-tests of its own operation. We cannot be sure what tests or what actions are performed within the SOUP processor, but the TT wrapper needs to perform continuous self-checks on its own operation to make sure that it is correctly generating verified outputs. And we'd use this correlator platform to achieve that. However, this isn't quite enough. IEC 62304 assumes that the software may fail. The phrase that's used, and it often causes some confusion, is the probability of a software failure shall be assumed to be 1. In other words, if the software in our medical device, we have to assume that it's possible that this software may fail. We therefore usually require some form of external risk control measure to provide confidence that the medical device will operate safely. In this example, our TT wrapper uses a hardware external watchdog controller, an EWDC, to achieve this. The EWDC is designed to move the system into a safe state if the TT wrapper fails to operate correctly. So our design now begins to look something like this. We have the processor running SOUP. We have the TT wrapper running our known correlator software platform. We have an external watchdog controller connected to the TT wrapper processor. If there's a failure of the TT wrapper processor, then the EWDC will ensure that our pump is moved into a safe state and that no harm can come to the patient. So we have here what's sometimes seen as a complexity sequence. So we have our processor running SOUP. This may be a complicated design. This processor may be running Linux, it may be running Windows, it may be a complex multi-core processor. There may be a lot going on here. We then have our processor running the TT wrapper. This will typically be a qualified processor. For example, a SIL3 processor, or possibly even two SIL2 processors performing the safety checks here. Finally, we have our EWDC as the last step in our complexity sequence. So this is a hardware-based mechanism, a watchdog type device that has to be fed by the TT wrapper processor. If it's not fed by the TT wrapper, it pulls our system into a safe state. So our complexity sequence looks something like this. Our processor running SOUP may be potentially extremely complicated. Our processor running the TT wrapper will typically be of very limited complexity, highly deterministic behavior, can be modeled precisely and monitored precisely at runtime. And then finally we have our very simple EWDC, our external watchdog controller mechanism that provides a final safety net in our system. Now, you may be wondering if there isn't a simpler option here. We've got our processor running SOUP. We know that we cannot directly send the SOUP outputs to our pump, but couldn't we use an external watchdog controller on our processor running SOUP? If we did that, then potentially the EWDC could detect when the processor running SOUP wasn't operating correctly and could shut the system down. And we wouldn't in these circumstances need the additional complexity of the TT wrapper processor in here. The problem with this option is that it simply wouldn't be acceptable. We have no knowledge of what level of diagnostic coverage would be provided by the EWDC in these circumstances. In other words, and this is the key challenge, the SOUP could potentially fail dangerously but still feed the EWDC and therefore still send potentially unsafe outputs to our infusion pump. This is simply not an acceptable solution. So we're going to have a situation where we have the processor running SOUP. We're going to feed the outputs from that processor through our TT wrapper. We're going to send the verified outputs to the pump. In this case, the diagnostic coverage provided by the TT wrapper can be fully assessed at the design stage and during the test and verification process. So what we're typically going to do is we'll have the SOUP processor performing a set of frequent periodic tests and reporting the results of these tests to the TT wrapper. So we'll program the SOUP processor to perform a set of tests and report those results to the TT wrapper. If the results obtained from the testing don't match the expectations at the TT wrapper, the system will be shut down. So the TT wrapper, as already mentioned, also contains comprehensive self-monitoring. The overall end result is that we can demonstrate that the risk that the TT wrapper will still feed the EWDC and potentially, therefore, give rise to incorrect outputs being fed to the pump we can demonstrate that the risk of this is very low. So that brings us to our conclusions. In this presentation I've considered what IEC 62304 is, considered what SOUP is, and I've summarised some of the links between IEC 62304, IEC 61508 and time-triggered or TT architectures. I've tried to demonstrate how some of the challenges of SOUP can be addressed by implementing a TT wrapper around your system. If you'd like further information about TT wrappers, please contact Safety Systems. Thank you very much for watching this video.